Sure.
Okay, cool. So our stream is up and running. So let me begin by welcoming everyone today to the Friday Noon Talk. Today's speaker is Dr. James Renaud. James and I were actually classmates in the medical physics program at McGill. James did his master's and followed up with a PhD at McGill, and then moved on to a postdoc position. Correct me if I'm wrong, your postdoc was at McGill, and then you transitioned over to the National Research Council in Ottawa. That's right. And then you've recently been made a research officer, specifically in the Ionizing Radiation Standards lab. So with that, we're honored to have you here today to talk about some of the work you've been doing at the NRC. So I'll hand it over to you, James.
Thanks for that. All right, so morning, everyone, or I guess, yeah, not quite afternoon yet. So I'm going to cover some of the work that I'm currently involved in here at the NRC. And this involves in developing a new primary standard for noble radioactive gases. And the methodology specifically is based on length-compensated internal gas counting. But I'm going to really take my time and build up to this because there's a lot of interesting, I guess, context for this type of for this talk, and I think just for the students as well, it might be beneficial to just gain some context for all these concepts. So starting from the beginning, so we refer to the National Research Council as Canada's National Metrology Institute. But what is metrology exactly? So we're all, we make measurements every day, whether we weigh ourselves in the morning or we take our temperature because we're checking for a fever or something, blood pressure, speed on your car. We measure all the time, and we take a lot of it for granted. But the ability to measure something is insufficient on its own. You need standardization for a measurement to be meaningful. Metrology, formally, is the scientific study of measurement. So it establishes a common understanding of the units. It links this to human activities, and it has far-reaching implications for industry, all areas of trade, quality of life, and not to mention science and innovation. So the objectives of metrology are to realize measurements that are stable, that are comparable, and are coherent. So one, we want stable measurements because long-term trends can be used for decision-making. Two, we want measurements that are comparable because it permits different laboratories, different groups of individuals to come together and actually compare results. And we want measurements that are coherent because we also, in addition to different groups of individuals, we also want different methods to be brought together and provide that, build that confidence. So metrology has wide-ranging impacts on virtually every sector: economics, energy, environment, healthcare, manufacturing, industry. I could go on and on and on. After all, to facilitate trade between countries, there has to be some agreed upon system of measurement. It makes the world go around. So let's take a stroll down history lane. Keep this interesting. So actually the first recorded permanent standard was in almost 3000 BC. So this was the Royal Egyptian cubit, which was carved from black granite. And it was decreed to be the length of the pharaoh's forearm plus the width of his hand, which I was not aware of. And replica standards were given to builders. And interesting note, the success of the standardized length for building the pyramids, it can be seen by measurements of their lengths. So the bases differ by no more than 0.05%, believe it or not. And so cubits of various lengths were employed in many parts of the world in antiquity, is my understanding, not just strictly Egypt. Modern metrology, on the other hand, has its roots in the French Revolution. So as someone with a French last name, this is a natural fit for me. so the political motivation at the time was to harmonize units throughout France, and the length standard based on a natural source was proposed, from which all measurements would then be derived. So if you had to stop and think about it, how would you come up with a standardized length from scratch? So how would you go about doing it? So I thought about it and I thought, okay, well, I think the first place I would have considered was some sort of pendulum. And apparently that's what they considered, or at least one of the things that they considered, basing everything on a time measurement, and to derive the unit of length from the swing of the pendulum. Unfortunately, because techniques weren't sufficiently precise, and because they couldn't be reproduced with an absolute certainty due to the Earth's gravitational field at different locations in the Earth, the method was ultimately rejected. So in 1791, the meter was defined based on the distance from the equator to the North Pole. And this eventually led to the creation of a decimal-based metric system, and establishing standards for all other types of measurements that would come. So it's about a century later, about 1875. So Canada exists at this point in some form. 17 nations got together at the what is referred to as the International Conference on Weights and Measures, and it led to the signing of the Treaty of the Meter. And part of that was to establish what is known as the International Bureau of Weights and Measures, located in France, the Bureau International des Poids et des Mesures. And within this structure, committees were appointed to construct permanent meter bars and kilogram standards, and the best of which were chosen to be ultimately be the ultimate authority on length and mass. And these were actually kept for a very, very long time in an underground vault beneath France. Although the BIPM, the Bureau of Weights and Measures, although the original mission was to create an international standard for units and measurements and relate them to national standards to ensure conformity, in the years of passed since, the scope's been broadened to include electrical and photometric units, and as well as ionizing radiation measurements. So this all falls underneath that one organization's mandate now. So the International System of Units, or the SI, is a modern form of the metric system. It was established in 1960, and it's been updated periodically since then. And it's the only system of measurement in the world with an official status in nearly every country. So it comprises, it comprises, you can tell I'm reading some of this, it comprises a coherent system of units and measures, starting with the 7 base units, which are the second, the meter, the kilogram, the ampere, Kelvin, mole, and the candela. And the system is designed such that it allows for an unlimited number of additional units, derived units, as they're referred, to be represented as the products of powers of these base units. So of the 22 derived units that are provided with special names and symbols, amongst them are the becquerel, which is, you should be familiar within the context of radioactivity, the case per unit time. Another unit is the gray, absorbed dose of ionizing radiation, as well as the sievert, which is equivalent dose. So one last note is that recently, as recent as 3 years ago, the SI changed in a very fundamental way. It was redefined in effect. So these meter bars and these kilograms that were developed, these actual physical artifacts that were kept, under, lock and key, these have disadvantages, right? First, you could damage, you could lose, you could change the artifact in some way over time, thus changing your standard. And the other disadvantage of using a physical artifact is that you can't really benefit from advancements that are going to come in science and technology. So what happened about 3 years ago is that, following decades of intense work by many groups around the world, 4 of the 7 base units, so named the kilogram, the Kelvin, the ampere, and the mole, these were redefined in terms of constants of nature. So no longer would the kilogram be, dependent or defined as this chunk of platinum iridium. It would now be defined in terms of Planck's constant. The remaining three units, so the second, the meter candela, these were already based on universal constants before this. So it's really a fundamental change. It's difficult to grasp at the beginning why this would be significant, but the constants that the units are based upon are the same everywhere in the universe, right? So you have the speed of light, Planck's constant, elementary charge, Boltzmann constant, etc. And so the advantage of defining the units in this way is that as science and tech develops and you have new methods to realize these units, suddenly your definition can benefit from it. The units can be realized in theory, can be realized with an accuracy that is ultimately limited by the quantum structure of nature and our technical abilities, but not by the definitions themselves. That's the benefit, and it's taken me a little bit of time even to really appreciate this. It's, like I said, it's not something that's straightforward, and in terms of everyday life, this changes nothing. So, as an end user, I should say. So, if you're wondering what this redefinition, what the impact will be on, say, measuring dose in a clinic, the answer is that it had basically no impact whatsoever. So, as I keep narrowing my focus here in the talk a little bit, I want to just touch upon a few definitions just to kind of get some of this jargon, because I know a lot of jargon just gets thrown around, and it's taken me a few years to really understand some of these terms or get an appreciation. So I'm going to lay them out formally here. The first definition, which is a standard. So in metrology, a standard is an object or a system, something that bears a defined relationship to the unit of measurement of a physical quantity. So I'm going to use absorbed dose in this case as an example. So standards are the fundamental reference for a system of weights and measures against which all other measuring devices are compared. And there's a hierarchy to standards. So in fact, it's a 3-level hierarchy. At the top, you have the primary standard. And in the case of absorbed dose, at least in this country, the primary standard is based on water calorimetry. It's so all primary standards are made to the highest metrological quality, and they are the definitive definition or realization of their unit of measure. So it's sufficiently accurate so that it does not need to be calibrated. It's not subordinate to any other standard of the unit in question. So water calorimetry determines dose based not first principles, well, just above first principles. It doesn't, its calibration isn't dependent on the radiation quality. At the second layer, you have what is known as a secondary standard. And the secondary standard, these are generally more plentiful, less costly, but still serve as an approximation to the primary standard. An ionization chamber is a common secondary standard when it comes to absorbed dose. And these are calibrated with reference to directly calibrated against water calorimeters. The other important aspect to the secondary standard is stability and precision. Finally, the third level standard, the standard which is periodically calibrated against the secondary standard, is known as the working standard. We don't usually use the term working standard, as far as I can tell, in medical dosimetry. You might refer to it as a clinical reference chamber, or a local standard. But this is essentially the clinic's standard that serves to, say, calibrate all the linacs and is sent to the NRC periodically for recalibration. So working standards are expected to deteriorate and are no longer considered traceable to a national standard after a certain period of time. And working standards are used in the field to calibrate instruments. So if you think of, again, in the radiotherapy clinic, you may perform some sort of film based measurements, that film calibration is likely going to be traceable to your local standard, your clinical reference chamber. So thus providing traceability all the way to the primary standard in that way. So the second concept I want to cover is the concept of traceability. And so traceability is defined as the property of a measurement result whereby the result can be related to a reference through a documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So basically all that means is that there's a direct link between the different hierarchy levels within the standards to the instrument being used to perform the measurement. And that's said to have the traceability. And one characteristic is that with every layer of calibration, every link in the chain, you add uncertainty to your measurement. So the chain of traceability allows any measurement to be referenced to higher levels of measurement back to the original definition of the unit. And it's an important part. It really is an important part of the measurement. So one of the best ways to understand an instrument's measurement performance is to assess its accuracy. And the instrument should be calibrated against an SI traceable reference to ensure the quality of the measurement data. So quality data in turn provides reliable information for decision making. So one last definition I want to cover before we really get into some of the meat and potatoes of this talk is a National Metrology Institute. So the NRC is Canada's National Metrology Institute, and or an NMI for short. I'm just going to say NMI for short. The NMI's role in a country's measurement system is to conduct the scientific metrology, realize base units, and to maintain primary national standards. It provides traceability to international standards for a country, and it anchors the national calibration hierarchy. For a national measurement system to be recognized internationally, an NMI must participate in international comparisons of its measurement capabilities. So a few examples I have listed here: the Korean Research Institute of Standards and Science, so CRIS in South Korea, NIST in the US, PTB in Germany. Many countries have their own NMIs. And as I said, NRC is going to be the focus of this one. So I belong to the Ionizing Radiation Standards group, and our group's focus is on the calibration services and development and maintenance of primary standards within the realm of ionizing radiation. So we're located, our main campus, where our building is physically located, is in Ottawa, kind of east of downtownish. And here's a photo of our building, M35. And so within our group, we're roughly about 18 or so, if I've counted right, 18 or so researchers and technical staff, plus the visitors and the students and all the others. And really, our activities are centered around three main areas of measurement. So you'd probably be most familiar with the medical dosimetry. There's also industrial dosimetry, which is similar in a lot of ways, but at the same time, very different. Radioactivity measurements take up a large part of the activities here as well as performing neutron type measurements. And then I'm going to touch on all the facilities that we have here for your information. So in addition to these activities, we also have representation on all three of the CCRI groups. And our group is also responsible for the development and maintenance of the EGS Monte Carlo code system, which you may be familiar with. So a few of the facilities that we have here at M35. We're equipped with therapy level. Let me get this stupid window out of my face. So we're equipped with therapy level irradiator. For cobalt-60, we have two industrial / radiation protection level irradiators providing range of source strengths for cobalt and for cesium. as well as an electron microselectron brachytherapy afterloader with high dose iridium 192 sources, Hopewell free air chamber for low dose rate brachytherapy, and a wide variety of low activity radiation sources. The cobalt beams are standardized in terms of exposure, air kerma, and absorbed dose. Typical dose rates range between half a gray to a gray per minute. And these facilities can provide calibrations for therapy class ionization chambers, radiation protection devices, say survey meters, personal dosimeters, etc. The microselectron afterloader can deliver the iridium, the HDR iridium sources with air kerma rates of between 1 to 50 milligray meter squared per hour, and that depends on the time of year. And the HDR facility can also provide calibration services for the therapy class well chambers. We also are equipped with low and medium energy X-ray generators that provide stable beams of X-rays at constant potentials from 10 kV to 300 kV. Exposure rates covering both protection and therapeutic levels can be selected. The X-ray facility can provide calibrations, again, for therapy class chambers, radiation protection devices, as well as custom services, which can be arranged. The radionuclide metrology facilities consist of radiochemistry and decay counting labs. Radionuclide implements, some of the facilities implement 4-pi beta gamma, as well as the liquid scintillation counting primary methods, as well as a suite of secondary measurement detectors, radionuclide calibrators, solid state detectors, alpha spectrometry, etc. In the beta lab, 2 beta radiators can be fitted with promethium, krypton, strontium sources, which can have a mean energy anywhere from 70 to 670 kV. And they generate absorbed dose rates anywhere from 1 to 1,000 milligray per hour. So these rates are established with our primary standard setup, which is based on extrapolation chamber measurements. And the radiators are used for quality assurance testing of personal dosimetry systems and calibrating beta survey meters. This is a pretty cool room, actually. So the neutron lab at the NRC is really unique, and it's ideally suited for the measurement of low intensity neutron fields generated by sealed neutron sources. So you have this extremely large room with a false floor, and it permits calibrations and irradiation services to be carried out with minimal room scatter, essentially. Americium beryllium sources with typical activities of 25 gigabecquerel are available for the purpose of calibrating neutron survey meters, as well as independent testing of neutron dosimeters for QA. Now, this one's even cooler. The NRC Vickers, so it's a 1960s vintage electron LINAC, up to 35 MeV, high current short pulse machine. There's a variety of targets, flattening filters, collimation systems, scattering flow systems, beam current monitors, and beam steering systems, and it allows for a wide variety of clinical accelerator beams to be simulated. And being involved with this personally, I can attest that it's a really, really cool machine. The accelerator can be run with currents averaging less than a single electron pulse. In addition to the provision of electron and photon beams for dosimetry, the electron linear accelerator is available to outside users. That was a very formal way of saying that if you got a cool project and you need a cool machine, please give us a ring. Finally, we have 2 Electra clinical LINACs, and these are just standard, like off-the-shelf standard clinical machines. Photon energies between 6 and 25 MeV, 5 electron beams, and it delivers clinical dose rates of about 5. So just a standard clinical machine in that sense. So it allows us to do some clinically relevant research here on site. The newer of the 2 also has the onboard imaging capabilities, which is a new area for us. All right, so that ends my sales pitch, and I'm going to actually get into what we came here to hear about, which was radionuclide monitoring. And again, I'm going to build this up slowly and provide a lot of context. So please bear with me. The Comprehensive Nuclear Test Ban Treaty Organization, or the CTBTO, this is an international organization that's tasked with building up a verification regime. Basically, the CTBTO is a nuclear test ban, so they're looking to basically ban all nuclear testing. And in order to do that, it's also something that's not yet in force. So the preparatory commission is tasked with setting up the necessary systems that would be required to basically verify that everyone's complying with once the treaty is actually put into force. So the main purpose is twofold. It's to promote the entry into the CTBT and to establish a global verification system, which I've mentioned. And so this global system is meant to basically detect nuclear testing all around the world. Consists of different detection types of detection systems. Well, what I'm going to specifically talk about is the radionuclide monitoring stations, which are about 80 stations scattered across the globe. And the radionuclide monitoring systems, these monitor the atmosphere for airborne radioactive elements. So the presence of specific radionuclides provide unambiguous evidence of a nuclear explosion, and this is just a system that monitors around the clock. The radionuclide stations, they use air samplers to detect radioactive particles released from atmospheric explosions or vented from underground or underwater explosions. Roughly half of these, so about 40 of the stations, are equipped with so-called noble gas detection devices. So the noble gases are the focus of my talk. You probably are already familiar, but they're chemical elements that normally occur in the gaseous state, and their name, the noble gas, emphasizes the fact that these elements are largely inert and rarely interact with other chemicals. They're of particular interest in this context because during an underground explosion, even though most of the radioactive particles that are produced would remain trapped underground, noble gases are considerably smaller. And because they don't interact and attach themselves to, say, dust particles, they can actually seep through and then get picked up by the wind and then get detected at these stations. So they're of particular interest in this context. Because detection of underground under nuclear activities is particularly challenging. So in Canada, the responsibility for operating these radionuclide stations, this lies with the Radiation Protection Bureau of Health Canada. So Canada contributes this data from 4 stations located across the country, and 2 of them have this noble gas detection capability. The one in Yellowknife and I believe St. John's are the 2. Now, how does my work fit into any of this? Well, as it turns out, the problem is that there's a serious lack of radioactive noble gas primary standards and certified reference materials available to provide traceability to these monitoring facilities. And so what do I mean by certified reference material? Well, CRMs, as I'll going to be referring to them in this talks, these are controls or standards used to check the quality of metrological traceability of products, to validate an analytical measurement, a method, or the calibration of an instrument. A CRM is a particular form of measurement standard. And in this case, we're talking about samples of radioactive noble gas with known activity concentrations. So that's the part to remember in all this. So this is the focus of my work at present, the development of a domestic capability for the production and standardization of noble gas CRMs. So we're talking about isotopes of argon, krypton, and xenon. And all this to support the validation of current and to be developed measurement methods and instrumentation, as well as the qualification of operational measurement data used to support modeling activities and decision-making. All right, so getting into the actual detection technology. So length-compensated internal gas counting. First off, what is a proportional counter? Now, Peter Watson may cover some of this stuff with you guys in first year masters, I guess second year masters. But the diagram that you see here, this shows the relationship between a gaseous detection region. So say, I mean, you'd be most familiar with an ionization chamber, but this is only one of many different types of gaseous radiation detectors that you can have. So what it's plotting here is applied voltage compared to or against the charge collected. And they're depending on the voltage range applied, you have a detector that will behave in different kind of characteristic ways. The focus here is this so-called proportional region. So this is a region that's kind of adjacent to the ionization region that would be used in a typical clinical ionization chamber. So in the proportional region, the charge collected, this actually increases with a further increase in the detector voltage, while the number of primary ion pairs remains unchanged. So by increasing the voltage, you provide the primary electrons with sufficient acceleration so they can ionize additional atoms in the medium. The secondary ions form. These are also accelerated, and they cause these avalanches. As turns out, they're called Townsend avalanches, which I was not aware of. But each avalanche creates a large electrical pulse, which is then detected. So even though there's a large number of secondary ions for each primary event, the chamber is always operated such that the number of secondary ions is proportional to the number of primary events. So this provides a form of amplification. This is what the advantage is of this method. So in a typical proportional counter, you'd fill the container with gas, an inert gas, which is ionized by incident radiation originating external from the chamber, as well as a quench gas to ensure that the discharge terminates. It actually terminates because, as it turns out, if you don't have a quenching gas, you can have events that just basically produce spurious, I guess, avalanches and the pulses that keep going for a very long time. So a common quenching gas is composed of 90% argon and 10% methane. And this is known as P10. So in our case, the source of radiation isn't external. Because the gas itself is radioactive, it is the source of radiation and it's internal to the chamber. So the ionizing radiation originates from inside the chamber, but otherwise the concepts of proportional counting remain unchanged. So in length compensated gas counting, the concept is that you have a pair of chambers. We'll call them chambers. A pair of chambers, each containing cap regions. Each counter contains at its center a wire that would serve as an anode, and then the chamber wall itself would be the cathode. You would apply a high voltage to the anode wire, producing an electric field within your chamber. And in these cap regions, you'd start getting end effects. You'd start getting where the electric field is no longer uniform. So if you consider two of these chambers, only differing in terms of length, so one with length L and one with length S for long and short, but with identical caps, you can assume that the efficiency of the gas in the central regions where the electric field is kind of constant, the efficiency is, we'll assume it's 100%. And in the cap region where the electric field begins to deviate, it'll have some efficiency, so epsilon. To determine an activity concentration independent of the caps, you need to ensure that basically all four of the caps seen in this diagram are identical. So the same wire, same diameters, same everything. So the activity concentration is independent of the volume of the caps and depends only on the volume of the central regions and the count rates. So this requires multiple assumptions, and that basically is summarized by all the caps being equivalent. So looking at the equations here on the slide, the activity concentration will produce rates of count in the short and the long, differing only by the central region, the length of the central region. And then if you subtract those two equations, you get a difference in count rate. But suddenly the cap regions are then subtracted. They're eliminated, in fact. So at the end of the day, the quantity of interest is the absolute activity concentration, which becomes a quantity that depends only on the difference in rates and the difference in volumes. And again, the assumptions required for this method to work, excuse me, the main assumption is that your caps are equal, so that elimination in fact holds true. Digging a little deeper. So the first assumption is that the efficiencies in the central regions are the same. In other words, that all the decays are counted. So as I mentioned before, one important aspect is that all the atoms inside L or near cap can emit particles towards the cap, so that they do not deposit energy in L. So it's kind of like the concept of particle equilibrium. You can have decays that exit the region, but the idea is that you're going to have a compensation for decays that originate in your cap region, but then contribute to the region within L. So that's the one assumption that's being made. And then the second main assumption is that the four caps have the same count rate. And I've already gone over this, is that all four caps basically have to be manufactured in the exact same way. But from an engineering manufacturing aspect, this isn't too difficult to overcome. So one of the ways in which you can be sure that compensation for the end effects is being achieved is by looking at the difference in the count rate per unit difference in volume between a certain pair of counters as you change the voltage. So that difference should be produced basically a flat curve, even though the counts will increase as a function of voltage for both the short and the long. So at the NRC, the aim of my work is to calibrate the volumetric activity, or the activity concentration of radioactive noble gases using a primary method known as the triple differential proportional counter. So it's exactly what I just mentioned, but instead of having one pair, so two, a long and a short, you have three. So then you can produce three pairs of count rates, count rate differences. So as I said, it's a primary method. It doesn't require calibration via the radioactive sources. It consists of using three cylinders, three cylindrical proportional counters, and they all have the same design, same caps, The only difference is that, again, the lengths are different. So we refer to as the short, the medium, and the long. So the three activity concentrations are obtained by subtracting pairs of activities measured by each counter, divided by the difference in their volume. And the volumes are calibrated before the units put together. So that's done here at the NRC in a different by a different group. They specialize in say volume measurements among many other things, but what they do is essentially measure the amount of water that it takes to fill one of these wire chambers to determine the volume with a very high relative accuracy. So as a recap, the proportional counters are filled with a mixture of radioactive gas and P10. Following radioactive decay by beta emission, the particles emitted ionize the P10, and the electrical charges created are collected by means of a high voltage across the wire in the wall. The signal given by the number of charges collected will be proportional to the absorbed radiation energy. And the number of detected decays per second is proportional to the activity of the radioactive gas present in the counters. In the design, you'll see here, each counter is mounted vertically, and this is to avoid sagging of the wire. The design contains inlets and outlets for the flow of the gas, as well as the electrical feed through, which provides the connection between the anode wire and the power supply, as well as the amplification circuitry. This is a bit of a simplified view. In reality, the three connectors are plumbed up in series. This is just a bit of a close-up of the actual wire chamber design, and as well as the feed through. So you see the wire in this cutaway image, this wire it's about 40 micron in diameter, but this is welded to a stainless steel pin, which is then passed through this conflat flange, normally used for vacuum type connections and so on. So that provides the connection to the outside world. This is the state of the system at the moment, which is, again, still under construction. But the yellow arrows indicate the flow of the gas through the system. And it flows in a, they're all plumbed in series so that the gas flows through all three chambers in that sense, and provides a homogeneous distribution of the radioactive gas as well as the P10 throughout the system. The detection system is only but one part of the entire counting system. So as you can tell from the previous photo, there's quite a bit of plumbing going on. So there's a whole gas handling subsystem to this, in addition to the detection system, as well as the data acquisition system as well. So it looks quite messy at the beginning, but in essence, you have, can you actually see my cursor? I assume you can. You have the gas coming in, it gets mixed, it's then circulated through the proportional counters. The temperature and the pressure are monitored throughout, but in a sense, this is circulated through. On the data acquisition side, you have preamplifiers that are collecting the signal from the anode wire. Also, in addition, they're also providing the high voltage across the anode. And this is, fed through the amplification, the single counting, the single counter, single channel analyzer. And basically you get pulses, discrete pulses that are then converted to a logic signal and counted. It gets a little bit more complex to that when you start getting into things like dead time and discrimination levels and stuff. But in essence, that's what you're doing, is that every time there's an event, an ionization, it'll produce a pulse, an electrical pulse, which is then detected and amplified and counted. The end goal of this whole system is to produce, to determine the activity concentration of the gas inside your system. And there's also also to produce the CRM. So there's going to be a portion of the gas handling system that contains the same gas that's being measured, so that it can then be removed and it can then serve as a CRM for whatever purpose. But that gas that's contained in that transfer vessel is then well characterized. That's the whole idea. So finally, I'm gonna wrap this up. If you remember anything, absolutely anything from today, just remember that a measurement is meaningless without an uncertainty. I've told that to the students that I've helped supervise, and I'm going to say it here now too. You need uncertainty on everything, especially in the context of research, and oftentimes it gets neglected. You got to at least make some effort to estimate uncertainties, because it expresses the spread of possible values associated with what you've measured. And there are two components to your uncertainty. There's going to be an uncertainty interval, so the width of and then also a confidence level. So how much doubt, a quantitative expression of the amount of doubt that exists with your measurement. So in the table that you see on the slide here, these are all sources of uncertainty, typical uncertainty budget for this type of for this detection method. They all contribute to the overall uncertainty. And there's currently in the world, there's about, I believe, 4 NMIs with extensive experience in internal gas counting. They use slightly different methods to prepare their gas and in actually counting. And so what I've done here is I've kind of provided kind of a blended average of their uncertainty budgets. This is not actually, like I said, it's just to kind of give you a rough impression of the real thing. It's some are better, some are worse, but it gives you a pretty good idea of where the main sources of uncertainty lie. And in general, the sources of uncertainty can be classified as either being an accounting uncertainty or gas handling uncertainty. So for the counting uncertainties, basically nuclear counting statistics, so Poisson statistics, apply here. So in this case, you've got multiple detectors. So each spectrum is extrapolated to 0. And what that refers to is that level of discrimination. So when you produce a pulse from an event, your system is going to have basically an acceptance window within which it will actually count it as an event, depending on where you set that discrimination level. That's referred to as the energy, because there's going to be a whole beta spectrum produced by the gas. Very small, very low energy events aren't necessarily going to be detected, depending on, at the very low end, they won't be detected. So there's a method in which you extrapolate, you change your discrimination level so that you can extrapolate all the way to 0 energy effectively, and to get a representation of the true number of decays in this case. So in general, this method is equivalent to the square root of the sum of squares of the count rates of the individual counters, which make up the difference in the counter. So it's a little confusing, but I mean, I'm going to leave it at that because I'm still kind of getting comfortable with a lot of these concepts myself. So, but I mean, this would be repeated multiple times. That's the other thing. So there is this really does qualify as a type A uncertainty. So you have a random component to the counting. On the gas handling side of things, it's a little bit, conceptually, it's a little easier to grasp. You basically need to know how much gas you're putting into your system. in effect, the number of moles that you're putting in. So presuming that your system pressure and temperature are stabilized, everything can be treated with the ideal gas law. And it's surprising how well that ideal gas law actually holds up in real life. So it comes down to uncertainties on your temperature, your pressure, your volume. And in a well-established system, the sample gas and the counting gas volumes are determined through gas expansions. So you'd have a vessel of a known volume containing gas of a known pressure, say atmospheric pressure, and then you introduce that to your system, you permit it to expand into your evacuated system. If you keep track of the pressure, you can then deduce the volume of your system. And this can actually be done with a pretty high accuracy. And this would, be done throughout as a form of characterization and constancy of your system response. And any modification to your system would require you to redetermine that system volume through this gas expansion method. So again, takeaway is that ideal gas law and this everything is done, quantitative dilutions and expansions with known volumes and pressures. So I'm going to wrap it up at that. I'm just going to say though that we are open to we're looking for students, a student, and it's kind of a unique situation, something maybe worth considering, something if you are interested, maybe it's something that we could discuss, but basically there's the core part of this project in developing a primary standard, but there's also areas in which we could push on the research side of things. So there are some proposals here, different directions for research. One of them is the use of liquid scintillation counting as a complement to the measurement that I described here. And so it's a unique experience, working in a government context on such a, it's a unique opportunity. So something I would encourage you all to think about. Like I said, the logistics are something else that would have to be discussed. But all that to say is that we are open to the idea of having a student. So I'm just going to wrap it up here. Thanks for your attention. I know it wasn't the most riveting subject, and that metrology can be a little dry, but I think at this stage for students to understand the importance of, just the concept of traceability, uncertainty, that sort of thing. This is so crucial. Anyways, I want to just acknowledge some of my colleagues here that have played a part in this project to date, and I'm glad to take any questions that you might have.